there's basically two theoretical definitions that you'll be asked on your next quiz or on your next, it'll definitely be on the final exam. Right? As your sample size increases, the statistics that you gather, and specifically what we'll be talking about is the mean. We'll just be looking at the average. But as your sample size increases, the mean will be a better predictor, you could say, a better index, a better predictor or index of the true mean. In other words, of the population mean. And I select one person, right? I randomly, let's say I randomly select one person. So your sample size is 1. Right? This would be the population here. If I just select one person randomly, they could be anywhere along this curve, right? I could randomly select somebody that's here, or I could randomly select somebody that's here. And this value might not be very close to the actual average, right? The actual mean is over here. Now, so this might not be a good predictor, right? Whatever your value is here, this could be any value. And so if you just randomly select somebody, you don't know if you're getting somebody that's average or somebody that's at the high end or somebody that's at the low end. And so this could be any value, right? Anywhere on the spectrum. However, if I take a larger sample, like let's say I take, well, like these two people here, right? Let's say I pick one person that's down here and the second person down here, and I take the average of those two values, I might get something that is, let's say over here. Especially if I had a low value and a high value, the average might actually be close to the actual average. And as you can imagine, as that sample size increases, so let's say I have, like 10 or 20. If I take 10 values, the average is more likely to approximate the actual average. And we can go all the way to 30, and we can pretty much say when we get to 30, it's basically like if this is a little bit off, this one's going to be very close. The average of 30 random people is going to be very close to the actual average. Right? Like very close. And again, not exactly. Maybe there's gonna be a little bit of a difference, but it's gonna be very close. And that's what they're talking about here. And so, that makes sense, right? You say that the bigger your sample size, the better your statistics are going to be, right? That's kind of another way of saying that, right? The bigger your sample size, large samples give better statistics. That's another way of saying it. But the problem with large samples is that they're expensive, right? What's good is they give better statistics, more accurate. But the problem with large samples, the problem with these large samples is that they're expensive and they take time, right? The bad thing about them is that they are expensive, right? The bad things is that they are expensive. They take a lot of time. And so a lot of what we're going to be doing, this forms the foundation of what we're going to be doing in chapter 7 and chapter 8, where we're trying to figure out what is the minimum sample size that you can have in order to be confident of your results. All right, so that's one basis of what we're going to be doing. The second part, or the second definition, is that regardless of the distribution of the population, so you can have a population of values that is uniform, or that is skewed to the left, or that is skewed to the right, or that is just random, right? Not all populations are normal, right? Regardless of population distribution, right? It could be skewed, it could be uniform, it could be random, etc. The means, or the sample means, as long as n is greater than 30, that's the magic number that we've seen before, 30, regardless of the population distribution, the sample means, as long as they're greater than 30, will be normal. That's a very powerful tool that we'll see in a second, will be normal distribution. Okay, so these are the two things that, if you know this, then you'll get the theory question right on the next quiz. Well, this is a classic example, and so if you understand this one, you should be okay. You know, when you guys are going to become designers, right? You're in engineering, design, and drafting, and one thing when you design a building is you have to design an elevator, and you have to pick what kind of cable you need, right? You need to pick what kind of cable and what kind of motor and that kind of stuff that you need to support your elevator, right? So if this cable, this is what you have to be worried about. This thing can only support 2,500 pounds. But you'll notice that when you take an elevator, they usually have a little sign that also tells you, they'll tell you this number, but the sign inside the elevator also tells you the number of people, right? How many people can you fit in this elevator? And in this case, they're saying 16. So there's a sign that says 16 people. Okay, this is pounds. This is the number of people. All right, so the question is this a good design? That's basically the question. Like, is this something that is good, or is this bad? Is this going to end up getting you in trouble? Like, do you need to get a bigger cable, or do you need to make a smaller elevator? Like, what is the situation here? So we can answer the first question here using what we already know. So this basically the stuff that we learned in 6.2, right? With the applications of the normal, this is something that you would have seen maybe on your midterm. right? Where you say, if you randomly select one person, what is the probability they have a weight greater than 156.25 pounds? Because we need to have some sort of stats. They say men or males have a normal distribution with a mean of 182 pounds, 182.9 pounds, and a standard deviation of 40.8. So we can put that information on here, right? So if we know the average here is 182, right? And we know the standard deviation is 40.8. What is the probability that one random person has a weight greater than 156.25? Well, we can figure that out by using a Z-score, right? So you mark it, 156 might be somewhere around here. Again, it doesn't have to be perfect, but you have to do this to make sure you answer the question properly, right? They want to know what the probability is that somebody is greater. And how do we do that? Well, Z-score. But the question is, what is the probability that somebody is greater than 156.25 pounds? So you take out your calculator, right? 156.25 minus 182.9 divided by 40.8. And you get a Z-score here of negative, which makes sense because it's lower, 6532. So then you use your Z-score chart, right? And your Z-score chart will give you everything over here. Right, this is what your Z-score chart is going to give you. And you find out, well, let's take a look. So negative 6.5. Yeah, 6.5. That would be, right, negative 6, and then 0, 1, 2, 3, 4, and 5. So 0.2578. 0.2578. So again, as long as you know that in that case you have to subtract 1, then your answer is 1 minus that. Right? To go back and answer your original question, gives you 0.7422. And again, you could use Excel for this, right? You could use Excel as well. You could say, again, I'm just showing you all the steps in the traditional method, but and if we were in a classroom, you would have to, if we were actually in person, this is the strategy you would use because students weren't allowed to use Excel before going online. But now that we can use Excel, you could say the answer would be 1 minus normal distribution, and then you just plug in. Again, as long as you know that you need to subtract 1, you're going to be okay. You put in your values, right? 156 minus, oh, sorry, not minus. And then 1. And that should give you the same answer, or at least very close. It's going to be a little bit different because of the z-score getting rounded when we use the chart, but it'll be very close. So let's take a look. Right, so here you have 174.3, or sorry, 0.7432. So it's a little bit different, but it's understood that this would be, they should be a little bit different because there's a rounding that takes place here, right? But either of these would be correct, on the test or on a quiz. Now, that should be review. The new thing is what happens when you get 16 people. So why are we using this number 156? Well, 156, right? Why would we be interested in this number? We're interested in this number because 16, if the total weight is 2,500 pounds and you divide that by 16 people, which again, that's the conflicting information. So that's the conflicting information that's on the sign in the elevator. Right? These are the two pieces of information that seem to be conflicting. You get this number. That's the average weight of all 16 people. Yeah. If you do that in your calculator, that's the number you get, 156.25. So they're saying, what is the chance, right? They're saying that if all 16 people get in there, if they're all males, what is the probability that they're going to break the elevator? Right? What's the probability that it's going to be greater than this? If you have 16 people, and the central limit theorem tells us that it's going to be very likely. It's going to be very likely that we're going to exceed this weight. Right here, you just have a probability that one person is going to be 74, but 16 people. Here's how you do that. So when you're using the central limit theory for part B here, right, we have a sample size of 16. The only thing we have to change is our z-score. So if you go back to your formulas, you'll see that there's a formula that we haven't used over here on the central limit theory. This is what I talked about in the theory part earlier on at the beginning of this class. Here is the different part, right? So we're saying that the new standard deviation is going to be the old standard deviation divided by square root of n. And this is going to have the effect of increasing your z-score. Right? If you lower the denominator, you're going to increase your z-score. And so that's what we're going to do. We're going to say the new z-score when we have 16 people is going to be the same as the old z-score, right? So you have the same as the old z-score times the square root of the sample size. So the formula, which is this, so the average minus the average over standard deviation divided by square root of n. If you do the algebra here, it rearranges to this. You'll recall if you divide by a fraction, it's the same as multiplying by the reciprocal. And so all you have to do is just take your old z-score. So what do we get? We got a negative 0. We already calculated this, negative 0.6532. And then we times that by the square root of 16, which is 4. And I get negative 2.6128. And when you look this up on your chart, or you can use Excel, let's use Excel just because you could use Excel if you do this. In Excel, you could say it would be equals 1 minus, and then you do your normal distribution. And then you can just put in your Z-score here. And then standardize it, right? Say 0, 1, and 1. And this will give it to you. This will give you your probability. Or you can just look it up right on the formula sheet, negative 2.61. Point 0.0045, which would be 99.55, right? 99.9955 would be the complement of this, right? So 99% essentially, or 99.5%. And we'll get the same thing here. So equals 1 minus binomial negative 2.61, 0 and 1 and 1. What did I do wrong? Number, well, not binomial, normal. What am I thinking? Normal distribution. There we go. Right? 99.5, same thing. So that's good. So that's what the central limit theorem tells you, is that you got to be careful because the probability, so the probability of one person is 74%. The probability of 16 people is going to be 99.5%. In other words, there is a 99.5% chance that the elevator will be overloaded with 16 males. So in other words, as you become designers and become engineers, what you're going to want to do is, in that case, get a better cable, right? You want to figure out the cheapest cable, like in other words, the thinnest or weakest cable that's not going to break. So you don't want to buy one that's too big, but you don't want to get one that's going to, cause a lawsuit because your elevator broke. So that's a good, nice, useful application of some beautiful mathematics right there.